1, we're going to look at polar functions. Polar equations allow us to define some interesting and important curves that would be difficult or impossible to define in rectangular form, y equals f of x. And so we're going to look at a connection between them and how this all works. So here we go. This should be a repeat from pre-calc, but let's see if you can remember things. So in rectangular coordinates, we have an x and a y. So here's some point xy. Here's the origin, and it just means I move over x units this way and y units that way to get to that point. Rectangular. Left, right, up, down. In polar, that same point is found differently. It's found in a distance from the pole, so this is not called the origin, it's called the pole. And we have an angle that we sweep, and then we have a distance that we travel, so r theta. We are r units from the pole, and we are at the angle of whatever theta is. So the connection between these two, being able to go back and forth and stuff like that, is here's the same point in a rectangular and a polar format, and you can see that you just simply have the right triangle. And since I have a right triangle in here from this, then I have all these connections going on. So x can be considered the cosine of the angle. Remember, cosine of theta is adjacent over hypotenuse, so I can solve that for x. And then y, okay, is the sine is y over r, and then I can solve for y, and I get this expression right here. So these are your conversions between x's, y's, and r's. R can be the Pythagorean theorem, so it's x squared plus y squared, the square root of that. And then we have a connection for the angle itself by simply taking the tangent of that angle is y over x. So these are our conversions between polar and rectangular that you're going to want to be familiar with. It's going to be used in later problems, so particularly this one right here, so be careful that you remember it, okay? Now, for the most part, we don't need to memorize the graphs of what they look like and all that kind of stuff, but it is useful and helpful in some problems if you do know what the basic curves are. So here are some basic curves and the equations that create them. Circles. You have your basic circle, r equals a constant. So if you say in a polar equation it says r equals 3, that just means you have a circle with a radius of 3. And it sweeps through, the angles sweep through 0 to 2 pi. Okay? If I have this format right here, where I have a sine or a cosine with an a involved, like this, then it's just a circle that sits on the axes, like so. Okay? And if a is negative, it would be over here, a is positive over here, and the angle only sweeps half the circle, half the unit circle, so we only go 0 to pi. If I go to 0 to 2 pi, I just go around the circle twice. That's another thing we want to keep an eye out for, is these domains, because it will help you with some problems coming up later on where we got to find these angles that we're sweeping. Here's a rose curve. This is another common one that you're going to see. Let me move this picture a little bit. The rose curve comes in two formats. You have an odd number of petals or an even number of petals. I've only shown you the 4 and the 3, but it's even number of petals or an odd number of petals. Look at the equations, they look almost identical. Okay, so how do I know if I have an odd number of petals or an even number of petals? Okay, it's based off of that number right there. So if that number is odd, then that's how many petals I'm going to have. And if this number is even, then I'm going to have 2 times that many petals. So if there was a 2 in here, then 2 times 2 would be 4, so I have 4 petals. Okay? So that's kind of how you do this. Know the symmetries, it will be helpful also. In this one right here, we have y-axis symmetry. Here would be x-axis symmetry. And here we have both x and y-axis symmetry for these. Notice that for an odd number of petals, I can sweep all these petals from 0 to pi, whereas in this one, I have to go around all the angles in the unit circle from 0 to 2 pi to create this. Some other circles that you're going to see. The limits on curves. it up here like that. And there's the other ones after this one. I don't know if I have it on the next page or not, but this little indentation gets flatter and flatter. Okay, is another one that you would have, but these are the most common ones that you will see the most on, especially the inner loop. A plus or minus b times the sine of theta. If a over b is less than 1, you're going to have an inner loop. Okay, so you want to make sure that you're kind of aware of that one. And we want to find out where this inner loop occurs, and we'll see some problems that deal with that. You're going to sweep between 0 and 2 pi on all these. There are many other polar curves, but these are the most common ones, and you should know these characteristics, especially what the equation looks like, and that has an inner loop if this is less than 1. Okay, let's see what's here. So I have an example of some problems that you're going to be asked to do with polar. Here's the first one. For r equals 2 times the sine of 3 theta, find the rate of change of r with respect to theta at theta equals pi over 18. Pi over 18. So let's go ahead and take a look at that and see how that's done. I have that written right over here. So let's go through that problem. So how do I take the derivative of r with respect to theta? Well, just like anything else. Okay, here's my expression right here, and we're going to plug in pi over 18. So we take the derivative of 2 times the sine of 3 theta using our chain rules and our trig functions. So we got 2 times the cosine of 3 theta, and then times the derivative of the inside, which is 3. And I want to evaluate that when theta equals pi over 18. So, plugging this in, I get 6 times the cosine of 3 times pi over 18, which is pi over 6. The cosine of pi over 6 is the square root of 3 over 2, which gives me 3 times the square root of 3, and there you go. Okay, let's look at the next one here. This would be like a multiple choice kind of a question. This right here will be one that you might see if it pops up on your free response. It could also be a multiple choice, but here we go. So what we need to do, find the rate of change of x with respect to theta. So here we took the derivative of r with respect to theta. How do I take the derivative of x with respect to theta? There's no x here. Well, that's where those conversion formulas come in. X is r times the cosine of theta. R is this right here. So you need to substitute that times the cosine of theta. See? Substitute the r in there. And now take the derivative of this. Okay? So then I now have dx d theta, and we take the derivative of this, we can see that we have a product rule here. First times the derivative of the second, derivative of this cosine is minus the sine, and then the second times the derivative of the first, which is going to be 2 cosine times 3, 6 times the cosine of 3 theta. So that is dx d theta. And you can simplify this out if you needed to. Just depends on what they want you to do next. Now to find dy with respect to theta, so y with respect to theta, and same thing. You substitute the value for r in for here. So that is 2 times the sine of 3 theta times the sine of theta, and then we take the derivative of that. Times the cosine, and then the sine, times all of this up here again. And there's dy. Okay? Again, if this was on the free response portion of the test, you would not need to simplify any of that out. You would just leave it. Okay? Next example. For r equals 3 plus 3 cosine of theta, find dr d theta and dx d theta. So dr d theta is pretty simple because it's already in r equals form. We just need to take the derivative of it. So this is simply going to be 3 times the derivative of the cosine, which is minus sine, negative 3 sine theta. Done. And just like the one up above, how do I find dx d theta? Well, x is r times the cosine of theta, which means I'm going to have 3 plus 3 cosine of theta times the cosine of theta. And I have to take that derivative, and I have a product. So 3 cosine of theta, derivative of the cosine is minus the sine, and then the second times the derivative of the first, which is going to be a negative 3 sine of theta. Okay, pretty straightforward. Here's another example of a type you might see on an AP exam. The polar curve is given by the equation r equals 10 times theta divided by theta squared plus 1. Theta is greater than or equal to 0. What is the instantaneous rate of change of r with respect to theta, where theta is equal to 2? And what they're doing is making sure you know the terminology that's used a lot. Instantaneous rate of change just simply means dr d theta, evaluated when theta is 2. So they want you to find dr d theta when theta equals 2. Okay? So it's about this word right here, these words. What does that mean? Do we remember what it was? So let's take the derivative of this. It's the quotient rule. So the bottom times the derivative of the top minus the top, derivative of the bottom, all over the bottom squared. And we want to evaluate that when theta equals 2. So now we're just plugging in 2. Okay? So we have 2 squared plus 1 times 10, 10 times 2 times 2 times 2. All over 2 squared plus 1 squared. Okay? And so we work this out and we can get a number here: 4, 5, 50, 8, 80, 5 squared, 25. So whatever this becomes, negative 30 over 25, and negative 6/5. Okay? And so there's that right there. Pretty straightforward. And what's another question we might have to do? Oh, this is the information, second derivative, sorry. So down here at the bottom, I forgot to do this bottom part down here, sorry. 2 squared plus 1, negative 6/5. I'll put that right there so you can see it. All right, so down here, second derivative. Finding the first derivative, dy dx, and the second derivative, of y with respect to x twice, given a polar curve. So we're going to write x is r cosine of theta, y is r sine of theta. Write in parametric form, dy dx is dy d theta, dx d theta, and so that's how we go about doing this problem, just like we did for parametric form. Okay, the second derivative then is the derivative with respect to theta of dy dx divided by dx d theta, so don't forget this on the bottom over here. And once we have this, we can now use this to find the slopes of tangent lines to polar curves and other equations. Second derivative talks about concavity and stuff like that. So let's take a look at some of those examples, which is what I had popping up right here. What is the slope of the line tangent to this polar curve at theta equals 0? Okay, so I don't need to draw this curve. We can and kind of see how it lays out, but we can do this problem without seeing the curve. And so how do I do that? If I want to find the slope of a tangent line, I need dy dx. Okay, so that means I have to find dy d theta and dx d theta. Cosine of theta which is 1 plus 2 sine of theta times the cosine of theta. And then I can take the derivative of that. And then y is r sine of theta, 1 plus 2 sine of theta times the sine of theta. So we can find dy d theta. Actually, let's just do it all at once. So what is dx, dy dx? Is dy d theta, dx d theta. So what is the derivative of this with respect to theta? Okay, and so we just go through that process. 1 plus 2 sine of theta times the cosine of theta, second times the derivative of the first, and then we take the derivative of the bottom. Again, 1 plus sine of theta and then the second times the derivative of the first. And we want to evaluate this when theta equals 0. So we want to evaluate this when theta equals 0. And so we just plug in all of our zeros. 1 plus 2 times 0, because the sine of 0 is 0. The cosine of 0 is 1. The sine of 0, cosine of 0, and then 2, 0, 0, 1, 2 times 1. Okay, so just plug it all in like that. And when you work all this out, you're going to get that's gone, this is a 2, this is gone, so you have 1 over 2, 1/2. And there you go. And here's my last question for this video. Find the second derivative of y with respect to x twice for the curve given by a polar equation, r equals f of theta. For this polar curve, it is known that dx d theta is this and dy d theta is that. So we want to find the second derivative of y with respect to x. So the first thing you have to do, obviously, is find the first derivative. The first derivative is dy d theta divided by dx d theta. Well, luckily for us, they gave it to us. Oops, wrong one. dy d theta, 2 times the sine of theta. Dx d theta is the cosine of theta. And at this point right here, you should look for identities that will help you out to simplify this if possible, because you're going to continue with it. So this right here, sine over cosine, is the tangent. So this is 2 times the tangent of theta. Much easier to deal with. If it's possible, you should do so. Okay, so now I want to find the second derivative of y with respect to x twice. And to do that, that is the derivative with respect to theta of dy dx. And then divided by dx d theta again. Don't forget this bottom part. What is the derivative of this quantity with respect to theta? The derivative of the tangent is the secant squared, so this is 2 secant squared of theta. Dx d theta is the cosine of theta. Clean this up because these are related to each other. Cosine is 1 over secant, which pops it up on top as another secant, and gives me 2 times the secant cubed of theta. And there you go. Okay, so those are some skills you're going to be asked to do with polar, and the next video will show you some more advanced processes you're going to be following. So that ends this video.